So there was a question asked about some optimization for queries, right? So there is a large table that part of this table needs to be cached as like a subtable where some queries will be run, right? And there will be queries run on a concatenation of first name, middle name, and last name, concatenated columns of a table. So they will be concatenated. So if you don't know if a given name is a first name or last name or middle name, then you can still search for this just using a single column, which is by itself quite a good idea. To optimize the queries, right, the user who asks the question also suggests that this cached values, they will be uppercase, right, so that you don't so that you have a case insensitive query potentially, which is also fine. However, the next step that the user wants to do is to call something like some operation which is not defined in Oracle really, ling, which I understand linguistically processed on this full name, so that the query can also take linguistic values into consideration. And now the actual problem begins, right? Because the user tried to create a column or an index, a functional index on columns using the NLSSORT values, and wants to, I understand, still search this column using the like predicate. And the problem here is, of course, that the NLSSORT function, which creates a collation key, is not directly compatible with the like operator. The NLSSORT function creates collation key, and the collation key can be used or is used to linguistically process only certain string operations. In particular, relational operators. So this is comparison conditions, is, I think, is the proper name in Oracle documentation. So any equality, less inequality, less or equal, less, greater, greater or equal, between, in, case, all these operations where the actual operation that is done on strings is to compare the whole string for equality or inequality. Any operation that actually does something like a pattern matching, which is, for example, a like operator, or the regular expression operators, but also translate or replace in string, right? This type of operations, they won't really benefit from NLSSORT. So they don't use the NLSSORT function. And because they don't use the NLSSORT function, they an index on NLSSORT function won't help much. There is actually a small optimization that internally uses NLSSORT for the like operator for certain scenarios, where what you search for is a prefix, but this is only used to reduce the range of rows, the set of rows that will be actually processed with like, right? So you can, if you have a prefix operator, you can say, oh, okay, you don't need to look at certain strings smaller than the prefix, and you don't have to look at rows which are larger than the next value, linguistically directly larger than this prefix, only between these two border values, you need to look into the actual NLSSORT, the actual like pattern, right? But this is a certain optimization that the optimizer can do. For a general like, and in this case, the application would need to do such general like, because if you concatenate three names and you look for a name, right, then of course you need to use a pattern which starts with the percent sign and ends with a percent sign, because otherwise the whole trick of finding the name as first name or middle name or last name won't work. But it means also that NLSSORT is not useful for this purpose at all. You actually, so the answer is, you actually just need to do a normal like on these values. The question is, of course, there are some more optimizations or normalizations in addition to upper than you may want to do to make some simpler search, right? But of course, generally, if the idea is to look for accented and non-accented names, for example, so you need an underscore AI sort, then you need to run a like operator on the original string, and you cannot really speed this up using an index unless you actually create a binary index, and the standard binary index can be used as a source of data, right? So instead of looking at all values in a row, if rows are very long, so in addition to first name, middle name, and last name columns, there are a lot of other columns that need to be cached as well, right? So to not have to do a full table scan on this cached table that are discussed here, you may just want to do a scan only on the column itself, in which case you may want to create a binary index, and then the optimizer will use a full index scan and not full table scan. And such full index scan, if the index is done only on a single column, which will be much faster than a table scan, because there is much less data to be searched. Of course, if the table actually has not much columns in addition to first name, middle name, and last name, then there will be no real gain from using an index. You can just use a full table scan, because we are already talking about a selected number of rows and some 7,000 rows, as I see in the question. So, in short, all these operations that the user tried with UTL row and trying to do anything on this raw value, it won't help with a like predicate. You can only use it effectively for a comparison condition. If my answer is not clear, then of course please ask the question again with some more detail, and then I will try to answer it the next time, or answer it through AskTOM or directly as well, if there will be no direct I mean no office hours coming in the nearest future. I can also answer this out of office hours. Okay. Okay, I just wanted to show a live SQL query for NLSSORT, just that we can maybe use this time to quickly analyze what's in the NLSSORT value. Okay, so let me share Here is the window. Okay, share. Okay. So I hope you can see the screen. So I've just run a simple query on a few values. All right. I will actually add another one so that we can quickly look at how such collation key looks like. Right. We see that these values, right, look even for a single character kind of strange, right? This is because they separate a single character into something that we call weights, right? So the character uppercase A, actually this is I think lowercase a. Let me do a small trick because I see that it gets lost by automatic uppercasing. Okay, here we have actually the small component. All right, and then this one. Let's run this query. And then here we see now that for the small letter A, right, and for uppercase A, we have the main weight because we want to sort all strings that, let's say, for example, begin with A, right, close together. So we want to have these binary values that are compared instead of the original values, right? So the linguistic comparison uses the collation keys in place of the original strings to get the order, right? So if those two strings sort binary in a certain order, then this is the order that the original strings will take in whatever sort was used. In this case, the sort Polish, right? This is actually a Polish letter A with ogonek. This is a Polish word that is also used in English to name this hook under the letter, and ogonek is actually, as it means in Polish, small tail. So it's an A with small tail. So we see here that the main weight for the letter A, lowercase and uppercase, is the same. However, the minor weight for these two letters is different, and actually uppercase will go before lowercase. There will be some languages, so sort orders where actually lowercase come before uppercase, in which case here you would have a smaller number than you have here, right? So we have separated the weights of certain properties of the letters so that we can group all A's together, and only if they are already sorted together because of the main weight is the same, we can further in the comparison compare their case and then decide based on case which one goes first and which one goes second. Here we see that for ogonek, the main weight is higher because in Polish language, this letter A with ogonek, which is pronounced on, so this letter on actually sorts after A as a separate letter. It's not treated as a almost A just with an accent. It's actually a separate letter that will go between A on 4 and B, which actually have a much higher weight, which is 1A. This is hexadecimal, so this is 26, right? And here the same, right? These two letters, just differing by case, have just differ by the minor weight, and these two also. Here we see that if we try to calculate the collation keys for a string which consists for multiple letters, then the function NLSSORT, which produces the collation key, will first concatenate the major weights, so the more important weights, and you will get A on B, A on B, right? Then there will be this zero byte, which is just a separator to separate major weights from minor weights, right? And then you have minor weights concatenated, and there is another separator at the end. We have more complex sorts, like multilingual sorts or Unicode UCA-based sorts, in which case we have actually more than two types of weights. So here in the monolingual Polish sort, we have just a major and minor. In multilingual sorts, we have primary, secondary, and tertiary, where primary encodes the main letter, the base letter. Secondary encodes the accents, any accents that are sorted close to as like a lower priority property, and then the tertiary are for case. And there are actually some that have either quaternary weights, but these are specific for East Asian sorts. However, so here we see that the collation keys for a string cannot be viewed as a simple concatenation of collation keys for the letters. And this is exactly why, if you try to do any type of pattern matching on the collation key, you won't get any reasonable result, right? You will only this can be only used to compare two binary strings with this in the same collation, so that their mutual ordering will correspond to the expected mutual ordering of the original strings for which the collation keys were produced. However, you cannot do really anything on the character level from such a concatenated value. So I hope this clarifies a bit more about why NLSSORT is not suitable to for use for certain operations, string operations that still require linguistic processing, but which are not simple comparison operators. Okay, I see a question. Just index SS. Yes, exactly, right? So the question is, why not just for the original question of the posted by the user that I talked about previously? Why not just index the column as is and rely on the collation features of for language sensitivity? Yes, this is exactly what I said, right? We can just index the column as is binary, which gives us an index which is a sort of data, and then if we just run a like operator on it, then linguistic like or whatever other operator, then this index will be used as a source of data. However, it won't speed up any exact search. So it's not like if we do like whatever predicate, we will actually get just 3 rows from the index. We still will have to do a full scan of the index and linguistically apply the pattern for like or in string or some other operation to each of the value that we have read from the index, right? As I mentioned, there are certain patterns for which the like operator is actually optimized. For those, would make sense to create an index on the NLSSORT value, but if most queries are actually not expected to have a prefix pattern, so the pattern that first has a some literal value and then has the % sign or underscore sign, then creating such index makes no sense and just makes inserting data into the table more expensive. Another suggestion, Oracle text index. Yes, for certain types of queries, certainly Oracle text index may help. I must admit, I don't quite remember how far the Oracle text does the linguistic features that we have in the standard indexes, but I think they have something like base letter matching, so that you can actually match independently of the case and of the accents. However, of course, an Oracle text is a heavyweight index, so depending on the expected performance, I think that in the original question, the number of cached rows is 7,000 only. 7,000, I think. Okay, so yes, the 7,000. So for 7,000, creating an Oracle text index may not be optimal. As usual with performance, doing a benchmark is best idea. So the suggestion is that Oracle text can store certain substrings for prefix chain, several substrings to several lengths, maybe for various prefix searches. I guess so. I'm not an expert in Oracle text, unfortunately, so I would have to check. But certainly, so without doubt, Oracle text is much better index for a lot of text operations for more advanced searching, right? So if you really need some proximity searches, substring searches, any searches that find similar words where the similarity is not just by difference by accents or case, right? So some more complex, even synonyms, right? Especially for, I mean, it's not necessarily available for all languages, but for some languages, certainly for English, there are a lot of features in Oracle text that make real life searches. So the searches that we are expected from Google, right? Much more viable. With standard searches, whether linguistic or binary, we are seriously limited to basically to certain substrings. So depending on what is the type of queries, then Oracle text may or may not make sense, because of course of certain costs of querying the index and accessing the table directly. So with 7,000 rows, it may not necessarily be a good idea. However, for certain types of queries, it may be the only way, right? Because if you may just need to have a contains predicate in a query. The like predicate may be not good enough to satisfy end user requirements. If the more complex query syntax of the contains clause is needed, then of course Oracle text is necessary in any case, independently of the performance.